Next, we are going to do the seventh problem, that is the summation n equal to 1 to infinity tan inverse 1 by n. Summation n equal to 1 to infinity tan inverse n. Tan inverse n. For that, we are going through what is a n here. A n is equal to tan inverse n. We know that limit n tends to infinity, tan inverse n is equal to goes to tan inverse infinity. This tan inverse actually for the arc theta, for the continuous function, for the 1 function, this is actually this pi by 2. This cannot be always 0. This cannot be 0. So we can say that limit n tends to infinity, an is not equal to 0, implies that by divergent test, this sigma n equal to 1 to infinity, tan inverse n diverges. Right? Next is sigma n equal to 1 to infinity n into sine 1 by n. Right? Here again I am taking an equal to n into sine 1 by n. Okay. നമ്മൾ ഇവിടെ ആകെ ഡൈവേർജന്റ് ടെസ്റ്റും നമ്മുടെ സമ്മേഷൻ യൂസ് ചെയ്തിട്ട് മാത്രമേ പഠിച്ചിട്ടുള്ളൂ. അതുകൊണ്ടാണ് ഇവിടെ ഈ ഒരു ബുദ്ധിമുട്ട്. ഇവിടെയൊക്കെ നമ്മൾക്ക് നേരത്തെ കണ്ട ചില ടൈപ്പ് സീരീസിലൊക്കെ റൂട്ട് ടെസ്റ്റ്, റേഷ്യോ ടെസ്റ്റ് ഒക്കെ പഠിച്ചു കഴിഞ്ഞു കഴിഞ്ഞാൽ ഇറ്റ് വിൽ ബി ഈസിയർ ദാൻ ദിസ് വൺ. ഓക്കെ. സോ ഐ എം ചൂസിങ് ലിമിറ്റ് n tends to infinity an. This is equal to limit n tends to infinity. Here limit n tends to infinity n into sine 1 by n, which is equal to limit n tends to infinity sine 1 by n divided by 1 by n, which is equal to sine, this is the 0 by sine 0 by 0 form, again differentiating n tends to infinity cos 1 by n into minus 1 by n square divided by minus result, and this is equal to limit n tends to infinity cos 1 by n. This is cos 0, which is equal to 1 actually, which is not equal to 0. So we can easily say that the summation diverges. The summation diverges. What about the next one? N divided by log n. Again take the limit as in the case of like these problem, limit an that will be, so that converges to 1 actually, right? Sorry, that converges to infinity here. 1 derivative of n, 1 log n derivative 1 by n, that will become n as n tends to infinity, that's equal to infinity, not equal to 0. So that will diverges. What about this one? This is 2 by 3 whole raised to n minus 5 by 3 whole raised to n. 2 by 3 whole raised to n, this is a geometric series. Here the common ratio is less than 1. Here the common ratio is greater than 1. So this series converges and this series diverges. Together they diverges. Okay. So we will do some more problems from the textbook. Okay. We are going to do next chapter in this. There is a 9.3 integral test. 9.3 integral test. Okay. In this mainly two theorems in this integral test, and I have written already. In this test, in this chapter, they included the integral test and P series. The theorems related to these two. Theorems and proofs related to these two. In this chapter, they included integral test and P series and their problems. Theorems related to this integral test and P series theorem about the convergence and divergence of the P series, and that is included in this chapter 9.3. And after that, that will be comparison test, and we will introduce an alternating series, and after that, absolute convergence. Right. So we are moving to the integral test. What do you mean by an integral test? Okay. We can look through the textbook. This is the integral test. The integral test is defined as, this is the integral test. Suppose that f is continuous, positive and decreasing function on closed 1 infinity. If f of n equal to an for n greater than or equal to 1, then summation an and integral 1 to infinity fx dx either both converge or both diverge. Suppose that f is continuous, positive and decreasing function on close to 1 infinity, and if f of n equal to an for n greater than or equal to 1, then the summation n equal to 1 to infinity an and integral 1 to infinity fx dx either both converge or both diverge. In order to find the convergence or divergence of behavior of this series, we need to find out the value of integral 1 to infinity fx dx. This converges if it have a finite value, and it diverges if it values goes to plus or minus infinity. Okay. The proof is here. How will you do the proof? Right. Integral test is the proof is for f of an equal to f is continuous, given that f is continuous, positive, decrease. We have to prove this integral test. For that, in order to consider this, look at the picture. Consider the graph y equal to f of x. I will show in the notebook. Okay, this is the graph y equal to f of x. First, I am considering this picture. This is a graph, right? I'm choosing these points 1, 2, 3 up to n, right? So next I have to sum this n up to n. For 1, this is the image. This is 2. This is 2. A2 is equal to here. A2 equal to f of 2. Okay. So this distance is 1 unit, right? And also consider that this rectangle has width 1, right? The area is equal to this is a A2 actually. A2 into this 1. So area is equal to area of this rectangle is equal to area of this rectangle. Area of this rectangle, this length is equal to A2 actually, f of 2. And this is 1. So area of this rectangle is equal to A2. Area of this rectangle is equal to A3. This is A4 and so on. The last one is equal to, this will be AN. So area, the summation A2 plus A3 plus etc. plus AN. This is a summation of these areas, right? This area must be less than or equal to integral from 1 to n fx dx, isn't it? Is it correct or not? Yes, it is correct. Why? This is the integral meaning means that there is the area under the curve. So this is not included in our summation. So this A2 plus this is always less than or equal to integral 1 to n fx dx. Okay. So this is I'm adding this a1 on both sides, a1 plus etc. plus an less than or equal to a1 plus integral 1 to n fx dx. So look there what they have done in the proof. This is Sn, this is less than or equal to this one. So Sn is less than or equal to a1 plus what is the value? Suppose that this is convergent. Suppose that this integral is convergent. So this will be suppose that this is convergent, then this will be a value L. So this is Sn actually. Sn is less than or equal to a1 plus L, which implies Sn is sequence Sn is bounded above. Next, that is bounded above, and we have to show that that is single or equal to a1 plus L. That means the sequence is bounded above, and again next we have to show that this is increasing or decreasing, right? So Sn plus 1 is equal to Sn plus an plus 1, which is greater than or equal to Sn. So an plus 1 is equal to, this is greater than or equal to Sn means this is always greater than 0. So we can see that sequence Sn is increasing, right? So we have got that the sequence Sn is increasing and bounded above. So what happened? This is the result in this. So the sequence An is convergent. Sequence An is convergent. If we look through the next one, that is next graph, that is this is y equal to f of x. I'm considering this is 1, 2, 3, etc. and minus 1 n. Okay. Suppose I am choosing these rectangle in this, that is the greater rectangle, right? I'm choosing these rectangle. This is f of 2 here. When we are adding these rectangle sum, then that area will be, this is a1 plus, this is actually this is 1 unit, and this is the length a1, actually a1 plus etc. plus an minus 1. This is always greater than or equal to integral 1 to n fx dx, 1 to n fx dx. Okay, so that is integral 1 to n fx dx is less than or equal to a1 plus etc. plus an minus 1. So integral 1 to n fx dx is less than or equal to yes, that is a1 plus, I'm adding an on both sides, so an plus an less than or equal to a1 plus etc. plus an. So this is, if this is divergent, then that will be, this is actually less than this our series. So if this is divergent means that converges to that goes to plus or minus infinity. This is goes to plus or minus infinity. So this goes to again diverges, right? So this is the proof in this. Okay, you have to look through the textbook from this. Just listen. So what we have done, we have to consider these two graphs. Take the sum, lower sum and upper sum. The lower sum goes to, from the lower sum we can see that this sequence is, the series is convergent if the integral is convergent, and from the upper sum we can see that the series divergent if the integral is divergent. That is the result.